These are nice problems because they walk you through kind of all the examples that you might possibly have. Before we get too far into this, I want to mention the Van Hoff factor for each of them. When you've got words like this, like ethanol or like those methanol, like those kinds of words, those are going to be nonpolar things. Not nonpolar, I'm sorry. They're going to be non-electrolytes. When it has this format, like an element from the periodic chart or like an element in a polyatomic ion, those are electrolytes and they can split apart into things. But over here, like you get a word like that, or if you get the phrase non-electrolyte, then your I value for this one is 1. Now for this one, Na will break up in NaCl will break up into Na plus and Cl minus. So for that one, your I factor is 2. And then this one, aluminum on the periodic chart, if you look at where it is, it's plus 3. And then notice the 3 here. This guy on his own is just minus 1. So there really are 3 NO3 minuses in here for every one of the molecules. So the I factor for this one is actually going to be 4. The other thing is to remember the equation. So if we are trying to figure out the temperature change for a boiling point, then it's going to be your I factor times your molality times the appropriate K value right there. So this is for the boiling. And then it's the same setup, equals I times molality times Kf. But remember that this will decrease your freezing point. And if we're talking about water, the freezing point is 0. And this will increase your boiling point because solutions basically increase that liquid range for temperatures. And so solutions will have values that are higher than 100 or lower than 0. So let's go ahead and get started. For ethanol, it says that we're using 2 liters of water and that we're using 1 mole of each solute. If they'd given us a gram amount, you would just divide by the molar mass. So you'd have to have the formula or be given the molar mass of this one. This one, you might have this one memorized by the end of this course. This is going to be about 58 grams per mole. So if they had told us, 5 grams, you're going to have to convert to get to moles. But the point of this problem is just make sure to use the formula right. So that's how you would get it to moles. But we have moles of each, which is great because that gives us to our molality. So I'm going to go ahead and figure out the molality of all of these also, and then I can kind of set them up and do them all. So molality for this one is 1 mole of ethanol. A lot of times this is substituted with ETOH. Over, and this needs to be kilograms of solvent. So we have liters of solvent. So this requires one more thing, and maybe you wanted to see the word pure or something like that in there. Pure water at exactly 25, at exactly the right ATM, has a density of 1. So we're going to say 2.0 liters times in 1 liter, and this is grams, it's actually 1 gram is equal to 1 milliliter. That's the density of water. It's 1 grams per milliliter. So we're going to need to turn that into milliliters, and then we're going to say in 1 milliliter there is 1 gram of this. But look, the answer is supposed to be in kilograms. So hang in there. So if we go ahead and we bring this over, we know that in 1,000 grams, there's 1 kilogram. So look, your hundreds are canceling out. And that's because even though you saw this unit of density in Gen Chem 1, you can up all of the units and you can say that 1 kilogram is equal to 1 liter. Like that conversion will also work. So I could have skipped some of this and I could have just said 1 kilogram right here. So basically this answer is just giving us the kilograms. They're just hiding it in the molality unit. So that's the molality for that one. This one is 1 mole of NaCl over, and it's still that same 2 liters, which we know just converts to 2 kilograms of water. And then this is 1 mole of AlNO3, 3 over 2.0 kilograms. So now I have the problem set up and I'm going to work each of them individually.